Good morning, ladies and gentlemen. Thanks for waking up and joining me a rainy Monday morning at the end of semester. Today I'll be talking about metal-insulator transition. So just as every other normal class, we start by doing a recap. Let's quickly go over what we have learned about in Cattell's chapter 6 and 7. So in chapter 6, we mainly talk about the free electron gas. The electron, they obey the Fermi direct distributions, and this is how it behaves under different temperature. And then they fill up energy level called the Fermi energy. And then in chapter 7, we talked about the energy band. So electron, they feel this periodic potential from the atom and thereby changing their behavior to the block electrons. And this happens intrinsically because of the Bragg condition happen. And that creates energy gaps, and then it forms energy gaps, right? And then from the energy gap, depending on how much it's filled, the number of valence electron in the band, and also like the energy gap, you can determine whether it's a metal insulator or a semiconductor. So that's what we talked about. But is this statement really true? Is this how we classify everything? So let's quickly go over the history about the band theory. So everything started in the 1900s by Joule and Lorentz. So they came up with this free electron model, and then people after came up with improvements on the original theory. Sommerfeld came up with quantum statistics blog, which is Sommerfeld's student. He further improved and then invented this block theorem. But this is what we talk about, chapter 6 and chapter 7. However, in around the 1930s, people found a few conflicting cases. For example, the nickel oxide. It should be theoretically metallic based on the number of valence electron and other stuff. But actually, it turned out to be an insulator experimentally. But there are also other examples. So starting from 1949 and beyond, Mott and other people started working on the new theories for that kind of exception. So Mott had this hypothesis in mind based on Wigner's paper in 1938. The paper is here, and the Wigner is the Wigner from the Wigner seed cell. So he had this hypothesis in mind that there exists a critical lattice distance d naught. When the d is greater than d naught, the array is theoretically the array should be an insulator at 0K. If it's below this d naught, it's a metal. So this will be the paper that we will be mainly concentrating on. So, okay, the animation has a small problem. Anyway, so Mott's paper can be summarized in a single sentence. Basically, it explains how some material, they stops being metallic, not because of the energy gaps and stuff, it's because of the number of electrons, the number density. And then especially when the number density is not high enough. So let's start by looking at the Coulomb potential. So this is a classic Coulomb potential that we all know. And then when the Coulomb potential has a screening effect, we have another exponential decay term, e to the minus QR. And if you learned nuclear physics before, you will notice this looks like the Yukawa potential. It has the same mathematical form, but it's actually totally different. They have different origins. But anyway, so you have this screening factor, the Q, or the Q squared people. Sometimes people use 1 over Q, the reciprocal of Q, which is lambda. And this is given by the Thomas Fermi approximation. So you can see this Q is basically merely a function of n, like other stuff are all constants. So what happens when the carrier density becomes low? So when n becomes low, the Q squared for sure is going to decrease. And then the potential is going to decay more slowly, so it has a weaker screening effect, and the potential is going to be more longer ranged. So that creates the reason that electrons hop and jump between points because of they have overlaps in their wave function. The orbitals overlap. So once the potential becomes stronger at the original locations, the overlap gets decreased and that they become localized. So this soon turns into a roundaway problem. It will further reduce the carrier density, so it becomes more and more localized. So Mott came up with this criterion, Mott's criterion. Uncritical is the critical density of free electron times the Bohr radius. He used a weird notation. And A sub h is the Bohr radius. And if this number is below 0.25, it's an insulator. If it's above, it's a metal. And then he also deduced that in order for a system to conduct, you must create an electron and hole pair, and that costs energy roughly to half of the I minus E. I is ionization energy. E is the electron affinity. And there are typically two ways that you can excite either thermal excitation or optical excitation. But Mott's paper, the 0.25 is not the end of the story. There is still room for improvements. It's only valid for single valley situations. For example, 0.25 is only here. When you have different approximations and you have different valleys, you have different results. And by valley, I mean the number of energy minima. For example, there are 3 minima here. That's called a 3-valley semiconductor. And finally, a bit of history about Mott. So Mott was trained under Niels Bohr and Max Born, both great physicists, and he shared the 1977 Nobel Prize with P.W. Anderson and then Vleck. Even in his 80s, he was still publishing papers. And interestingly, Mott didn't have a doctorate degree, but both of his parents did. I don't know why this sentence bolded. I'm not trying to hinting at anything to you PhD students. But anyway, so this presentation perhaps marks my second final physics-related presentation in my entire life, my second one this afternoon. And then the Department of Physics at the University of Michigan gave me a hard time. We have one more hard time on the 29th. Is it final on 29th? Okay, one more. Oh, God. And then, yeah, please feel free to ask me any questions, as long as they're easy.
Okay, we do have some time for questions.
Which is great. Thank you.